this is the next problem. And I'm going to do this on 2 sets of panels here because this is really involved. Alright, so I have the definition here, defined here. We know that we have a curve of 64 minus x cubed. The x-axis, x equals 1, and x equals 4. Those are my 4 regions. Or not regions, those are my 4 lines that define my region. So those are my 3 curves, shall we say. This one, and that one. Okay? So for delta x then, I'll go over here since I kind of blocked myself on that. This is going to be 4 minus 1 over n, so that's 3 over n. And that will be my delta x. My CI then, I'm going to use, now, since you can go in either direction, you can pick the 4 if you want to. I will warn you, it gets really ugly when you start using really large numbers. If you start seeing cubes pop up in a problem, you might want to stick with 1. It's really easy to do. Not that your calculator is capable of it, but it gets really messy and a lot more punching in with large numbers. But do what you want. You want to experiment, that's great. But A here we said is 1. Delta x we said is 3 over n. So that is the value of CI. So, what's going to happen here then is we're going to deal with the limit. And as n approaches infinity, of course, infinite number of columns of the summation now, since I know that this is, well, I'm going to put in, we know that we're going to end up multiplying everything by 3 over n, so I'm just going to go ahead and put that right out there right now so I don't screw up and forget to do it for all of them. And that's probably what I should have done in the previous problem, just put that out in front. But I wanted to show you where that goes and how that functions and everything. But since these are both constant values, since n is a constant infinity, we're going to leave it right there instead of mixing it in over there. Okay? So now we come to this, and so this is going to be 64 minus, and now this is going to be 1 plus 3 over n for x to the 3rd power. That looks like a pi, it's an n. This is where things get a little crazy because I'll put a pencil out here and close the pencil out. Because now we have to FOIL that. But you don't have to FOIL that. And I'll show you a little bit here. Now, those of you out watching the video who have been in Scholastic will know what I'm about to do. Those of you who have not need to know this, because it makes life so much easier to FOIL things that are perfect squares or perfect cubes or perfect 4th powers or whatever, or binomials. Okay? So, there's something called Pascal's triangle. You may or may not have heard of this if you've not had Scholastic. Scholastic just gets inundated with this stuff. This is the tool that you will need to use for problems like this. And it goes like this. Pascal was a French philosopher slash mathematician slash scientist slash everything else. Yeah. He came up with this triangle. And this represents the 0 power of any number that you're working with. The next row begins and ends with a 1. And every row from now on will begin and end with 1. And then the next one like so. But this term right here is the sum of 1 plus 1, which makes that 2. And I'll show you in just a little bit how that can be used. The next row, 1 here, 1 here. And now you got between these spaces here, you put a number right here. 1 plus 2 is 3. 2 plus 1 is 3. And it continues on down there, and I'm not going to go any farther because this is as far as we need to go. So this is for 0 power problems. This is for first power problems. This is for second power problems. And this is for third power problems. And that's what we have here. We have here a third power problem. Now, what does that mean? Well, let's suppose that we had x plus y to the 0 power. What is x plus y to the 0 power? What is anything to the 0 power? The answer is 1. And that's why we have a 1 right here. Okay? What's x plus y to the first power? Well, anything to the first power is whatever is inside that parenthesis. So that's x plus y. The coefficient of x is 1, the coefficient of y is 1, 1, 1, 1, 1. First power problem. First power, what we call expansion of binomials. Okay? Next one. X plus y squared. Now, if you FOIL this out, you're going to get x squared for the first term. You're going to get y squared for the second term. And there is a third term. When you square a binomial, you are going to get a trinomial. And if you FOIL that properly, you're multiplying x times y and then y times x. So in other words, you're taking x times y and then doubling it, giving you 2xy. So your coefficients are 1, 2, and 1. Oh! Yeah. Yeah. So what happens when you have x plus y to the third power? You can now see the importance of using Pascal's triangle. You know what the coefficients are going to be. It's going to be to the third power, to the second power, to the first power, to the 0 power. But since we have two variables, it does the same thing in reverse. First power, or 0 power, first power, second power, third power. So we have x's and y's here. We put the x first. We're going to have x cubed and no y's. Because x cubed is the first one here, and y cubed is the last one here. And so there's this third power, this is 0 power, so there's no y right there. Plus. Okay? The second one then is going to be the second power. And I'm going to ignore these numbers for now, we'll come back to them. But I'm just going to show you what you should get for your exponent values. And what's happening here is the x's are going to be decreasing by 1 in exponential power, and the y's are going to be increasing by 1 in exponential power. So we have y to the 0 here, y to the first power here. The next one is x to the first because it loses 1, but y becomes y to the second. And then the last one is going to be no x's, and then y is going to go up 1, y to the third power. And I realize this probably made a mess of myself here by not leaving enough room for exponents or coefficients. So I'll do that. Oh, let's have a y there. Y there. Why? Because I want to. Now we put in the coefficients. Coefficient of the first term is 1. Coefficient for the second term is 3. Coefficient for the second term, or third term rather, is 3, and for the fourth term is 1, and we don't put the 1 there. And that is the expansion of x plus y to the third power. Now, what does that have to do with the price of tea in China in this problem? Well, I'm so glad you asked. We have here a binomial, 1 plus 3 over n. So that means x equals 1 and y equals 3 over n. Okay? So, that means then that this is going to be 1 cubed plus 3 times 1 squared times, what do we say that was? 3 over n, right? 3 over n, 3 over n. 3 over n to the first power plus 3 times 1 to the first power times 3 over n to the second power. Plus, now we have this y, that becomes 3 over n to the third power. Alright. Pretty snazzy, huh? So now let's just go ahead and simplify everything and then plug all that garbage in. 1 to the third power is 1. This is 3n times 3, which is 9 over n. Plus 3 squared is 9 times 3 is 27 over n squared, because we got a square for that n right there, plus 3 to the third power is 27 over n cubed. And that is our result of 1 plus 3 over n to the third power. And now I'm going to plug that in right there on the next page over here. So I'm going to slide over here, and this is what I'm going to have as a result. So I'm going to have limit as n approaches infinity of 3 over n times the integration of 64 minus, and then I'm going to plug that quadrinomial in there, 1 plus 9i over n plus 27i squared over n squared plus 27i cubed over n cubed. And of course we got I equals 1 here, and we're going to keep going on with that. So next thing I'm going to do is I'm going to change all these signs, because this is subtracting the whole thing, so I'll make that a plus, that becomes a minus, that becomes a minus, that becomes a minus, and that becomes a minus. And then I'm going to combine all that together, so I get 3 over n, I equals 1 to n, 64 minus 1 minus 9i over n minus 27i squared over n squared minus 27i cubed over n cubed. We can combine this. So let's do that, shall we? Again, 3 over n, I equals 1, 63 minus 9i over n minus 27i squared over n squared minus that time sign, 27i cubed over n cubed.